So let's return to what we were doing. Uh, yeah. So we were actually doing real analysis. So here's a continuation to the series discussion, sequences and series. So here we are going to look at the nature of series comparison test. We are given this kind of thing, that there is a uh, given series which has to be understood whether it is convergent or divergent or oscillating, whatever. And in this particular case, we will eventually see that the conclusion is either it is divergent or convergent. So there is a given series, namely u1 plus u2 plus u3 so on, which needs to be tested, and we are having a known series to which we compare v1 plus v2 plus v3 so on. So here's a proposition about this comparison test, and actually we are going to further generalize this to uh, a limit form, which is more often important, but let's see what is happening here. So let summation un and summation vn be two series of positive terms, meaning they are reals, such that summation vn is given to be convergent, and the relation between un and vn is each term in the summation un, that is, let's say first term is less than or equal to k first term of second term of un is less than or equal to k second term of the vn series, and so on. Of course, k is a positive constant, and we can also perhaps ignore finitely many terms. That is because we can always rewrite the given series with removal of first finitely m terms, let's say, but still we can conclude about the whole series even if the first m terms don't go by this hypothesis. That's not a problem. Okay, then the given series is summation un is always convergent. So proof, uh, without loss of generality, now we will assume that for all n this is true, un is less than or equal to kvn, and we are of course given that v1 plus v2 plus v3 plus so on, the infinite series is convergent. So let me take this thing, uh, small sn to be u1 plus u2 plus u3 so on up to un, which we have defined it as sequence of nth partial sum. Similarly, capital Sn is v1 plus v2 plus v3 up to vn, which we have defined as the nth partial sum sequence of summation vn. Now we are knowing something about this thing, not this thing, right? We are knowing something about the latter series. One second. So what I want to say is that so we are knowing something about the latter series, that this is convergent, and by the very definition of convergent series, the sequence of n partial sum converges, which means this limit is finite and unique. Let us give the name L. Okay, and we should conclude something about this series. Let's see how it goes. So I'm I'm considering this small sn. Okay, please remember this is small sn, which is corresponding to summation un, and so it is u1 plus u2 plus up to un. Now u1 is less than or equal to kv1, I said u2 is less than or equal to kv2, and so on up to un. right? So we can say this whole uh, partial sum is less than or equal to the corresponding terms of Vn. So we know something about this, so we will use that. So we'll take k outside and write as v k times v1 plus v2 up to vn. We'll take this outside the bracket, and then we know that this bracketed term is capital Sn. Right? Remember, capital Sn was the nth partial sum of summation Vn. So we conclude small Sn is less than or equal to k times big Sn. Take limit both sides, limit of small Sn and limit of capital Sn times k. Then we take k outside and we apply limit both sides. Now we know the right hand side. Right hand side is k times L because this guy converges to L. So scale, let's give a name capital L. So it is very clear that capital L being k times L, k being a positive constant, is finite and unique. Therefore, what we conclude is this limit is finite because L is finite. Anything less than L is a finite number. And of course, it's positive because all the terms being positive. So it's a finite positive quantity, something less than capital L. And therefore, we conclude that this is indeed the case that summation un is convergent. That's what we say here. Therefore, we have proved that the series to be tested is convergent. And now there's a limit form, before which I should have told that ditto the same proof works out for the condition if un is greater than or equal to k times vn, in which case this has to be the condition if summation vn is known to be divergent, if this is one condition, and also the second condition that corresponding terms are greater than corresponding terms in Vn, then we can conclude summation un is divergent. The proof goes ditto in the same way, except that you replace less than or equal to by greater than. Just replace that. So now that it is done, I'll erase this part. Now I'm going to come to the limit form. So the limit form, yeah, here's the limit form. Limit form is a proportion like this. Suppose summation un and summation vn are two series of positive terms, just like the other time I said, all reals. And suppose limit of un by vn as intention is a finite non-zero quantity. Now instead of just comparing, here we are saying what is going to be the uh, limit of un by vn as n tends to infinity. By the way, in the problems, you will have an expression for the nth term in given series. You will have an expression for the nth term in the known sequence, the series that we are considering. So we can in practice compute this limit. Uh, Suppose we get it as a finite quantity, non-zero, then we can conclude either both un and vn converge or both un and vn diverge. So there is a straightforward consequence of the main theorem that I just now discussed. But however, for the convenience of the readers, I'm going to do a short video on how this can be derived. But for now, let us be satisfied that if this box item is true, that the limit is a finite non-zero quantity, then un and vn, summation un and summation vn, either both converge together or both diverge together. So that's But let's take a small example. Let us discuss the convergence of this kind of a series. 1 divided by 1 times 2 times 3 plus 3 divided by 2 times 3 plus 4 times 4 plus 5 divided by 3 times 4 times 5 and so on. So you see these odd terms can be captured as 2n minus 1. These are odd terms, consecutive odd numbers, and these are consecutive naturals can be coded as n into n plus 1 to n plus 2. You quickly check that this really encodes this nth term of the given series. Now, what is to be compared it with? I said we should always compare with the known series. So let us take summation 1 by n square. In the class, I did tell you what is a quick way to understand the the preferable known series to be taken. Here it's a P series, and we know that this is a P series with P being greater than 1, and therefore this is convergent. Okay, so by hindsight, we understand what is the known series to be taken. So we have taken Vn to be 1 by n square. Let's see, when I put this in the numerator and this in the denominator and take the limit, what happens? See, I'm putting in the numerator 2n minus 1 divided by n into n plus 1 into n plus 2 and denominator 1 by n square. This is the Vn term and this is the Un term. Now when I do the limit, I have to simplify obviously. I first take this n square on the top. This 1 by n square goes as n square multiplied by 2n minus 1. Now I take it conveniently as n cube outside the bracket and write this as 2 minus 1 by n. See, 2 minus 1 by n. Similarly here, I take n cube outside and write this as 1 plus 1 by n, 1 plus 2 by n. Now I cut the two n cubes, and now you see as n tends to infinity, this term, let me write, you see, this term goes to 0, this term goes to 0, this term goes to 0. Right? So we are left with 2 divided by 1 into 1. So it is 2 by 1, it's 1. So that is how we got a finite quantity, non-zero, and which implies that the given series is convergent.